My name is Helen Mountfield. I'm principal here, and it's a great pleasure for me to welcome you to this evening's talk in our series of public talks, which is tonight our annual Jocelyn Bell Burnell Lecture. This is the night that we celebrate and show off about our relationship with Professor Jocelyn Bell Burnell, who, as I'm sure many of you know, is the great scientist who discovered pulsars as a doctoral student, thus winning her doctoral supervisor the Nobel Prize. And in 2018, just as I arrived here, winning a very well-deserved breakthrough prize, recognising the recognition she should have got then, and that she has had later in her career. She was telling me that when she was studying natural sciences at Cambridge, she did very well at geology in her first year and won a prize for it, and said she might be thinking about doing geology instead of physics. But her head of department told her that wasn't a subject for girls. So physics gain is geology's loss, and we are very pleased to have her as a fellow here. The other thing we celebrate about Jocelyn is how much dedication she puts into broadening physics and the study of science, and the interest and curiosity in science and belief in one's ability to engage with science for a wide range of people, including people who might not feel that they are naturally going to be recognised or seen as normal in that field, and that's a wonderful thing as well. And this evening, our speaker is somebody who does much the same, Professor Chris Lintott, who is, as he describes himself, a distractible astronomer who specialises in galaxy formation. He's a research fellow here in Oxford at New College, Oxford, but he also does a great deal in encouraging interest and excitement in science, using the Zooniverse citizen science platform and working in collaboration with more than 2 million volunteers around the world, building the Vera Rubin Observatory, which he says is going to power the next astronomical revolution, and maybe he'll talk to us about that, although revolutions sound to me quite planned, and he's talking about the accidental universe. But Chris is, as I'm sure you all know, also an author and a broadcaster on Sky at night, and does all sorts of stuff to explain physics to people who, like me, stopped doing physics a long time ago, but find it enduringly fascinating if it can be explained in a way that we understand. So thank you very much, Chris.
Thank you. Cheers. Thank you. Well, that's a challenge for the evening. I hope I will be understandable, but it's an honour to be here. It's a delight to be in Mansfield, which is a very special place, and to be giving this lecture named after Jocelyn, who's been an inspiration to me and to many others for many years. I have a principle in life, which is WWJD, which is what would Jocelyn do? And I also say yes to anything she asks, and so I am very pleased to be here. This is a talk really, it's an excuse for some stories, but it's really a talk about how science is done, because I think that the way we do astronomy, the way that I like to do astronomy, is very different from how it's portrayed by people on stages such as this one, at lecterns such as this one, or even in the media or in fiction. Really, astronomy is an adventure, it's an exploration, and the real breakthroughs happen when we stumble upon things. So let me give you an example. We'll start close to home, start with the planet Saturn, and Saturn's the best planet in the solar system. I would also accept Earth as an answer to that, but those are the only two right answers. The planet itself is amazing. It has the fastest winds in the solar system. It has this hexagon you can see at the top here around its pole, caused by ever-circling storms around its polar region. It has the rings, of course, which we think formed, actually found out in the last couple of weeks, it looks likely that they formed recently, in the last few 100 million years. They're thin, they're only 20 metres across, made of billions of icy particles in orbit around Saturn, perhaps the fragments of a once intact moon. And it also has an amazing retinue of moons, 120 or so at the last count, amongst them Titan, which is the only moon in the solar system with an atmosphere, a nitrogen atmosphere, a bit like Earth's, except instead of a water cycle, which we've become increasingly familiar with here in Oxford, on Titan you have a hydrocarbon cycle, where it rains things things like methane and ethane in raindrops the size of lawn tennis balls. And the good news, for those of you who've been outside in the last 2 months, is that on Titan the rain falls slowly enough that you'd be able to dodge the individual raindrops, which frankly seems rather useful. Anyway, Saturn is a fascinating place, and that's why it was the target for the Cassini mission, which is still the most sophisticated, complicated, over-budget mission ever sent to the outer solar system. Cassini went into orbit around Saturn more than 20 years ago now, and spent 17 years exploring the Saturnian system, looking at those winds, the rings and their dynamics, and with a particular focus on Titan. But the first thing that Cassini flew past was a small, obscure moon called Enceladus. And this is the best picture of Enceladus that we had before that mission, taken by one of the Voyager spacecraft in the late 1970s. And Enceladus is a ball of ice. It's about the size of the British Isles, fairly insignificant in solar system terms. And apart from the fact that people noticed that it was very shiny, it is in fact the most reflective natural object in the solar system, no one paid it much attention, to the extent that when Cassini flew past it, shortly after its arrival at Saturn, none of the instruments were turned on. No cameras took pictures, no measurements were made, with one exception. The British team, led by Michelle Doherty, who's now our astronomer royal, had an instrument which was measuring Saturn's magnetic fields. They're interested in how the magnetic field of Saturn interacted with Titan and perhaps the rings of this environment in the outer solar system. And they thought they would use Enceladus as a dry run for an upcoming encounter with Titan. So they took data recording the strength of the magnetic field as their probe flew past this obscure moon. And what they expected to see was absolutely nothing. There's no reason to believe that Enceladus should affect the magnetic field of Saturn. They got their data, they had a quick look, they saw that it was roughly what they expected, and I think most people would have stopped there. But Michelle's an excellent scientist. She wanted to make sure she had the best chance of getting results from the mission later on in the mission. And so they treated their encounter with Enceladus as a perfect dry run. They did all the hard work that you would do to calibrate observations if you thought you were going to make a career out of them. And when they did so, they discovered that actually something had happened. As Cassini flew past the moon, there was a change in the magnetic field. Something was happening around this icy ball that was affecting the magnetic field. And in fact, if anyone had looked, the same signature is in data from 30 years earlier, taken by the Voyager spacecraft, but no one had looked, so this was news. Another encounter with Enceladus was coming up. Michelle flew to California, to the Jet Propulsion Laboratory, to talk to the other scientists on the mission. She was the only woman who was leading an instrument. She was the only European who was leading an instrument. And she persuaded her colleagues that this discovery was so interesting that when they flew back past Enceladus, they should go closer, flying just a few hundred miles above the moon's south pole. And this time, they should take pictures. And this is what they got. This is the south pole of Enceladus, and those are fountains of water shooting up into space. They're now known as the fountains of Enceladus, and they instantly tell you that what seems to be a solid icy moon has a liquid ocean inside it. And because we've been able to fly Cassini, in fact it gave itself the first interplanetary car wash as it flew through these things, we could tell you stuff about the water. We could tell you, for example, that it's salty. And the fact that it's salty means that not only is there an ocean, but there's an ocean floor. So in other words, the water is in contact with rock. It's also slightly fizzy. It would be really good mineral water, I think, if you wanted to start a business importing Saturnian water, if you could get there. But that tells you there's an energy source in the ocean. And so suddenly this otherwise obscure moon became the place in the solar system that seems to have most of the conditions for life. It's an environment rather like the one in the deep sea, where we think life got started here on Earth. It may be that there is life on Enceladus. We don't know, but it's become an important astrobiological target, and the only reason we know about it is because Michelle's team stumbled across, did all the work, which you'll see will be important in lots of these stories, but happened to be flying past and taking data. And this, of course, has generated a revolution in how we think about places in the solar system. This structure of having an icy shell and water underneath is common, we think. So Jupiter's big moons, like Europa, which I'm showing here, at least 2 of them have oceans underneath, and there are probes on their way right now to Europa to investigate that particular place. So we have the European JUICE mission, which you can see taking off at the top there, and the Americans' Europa Clipper racing to the Jovian system to determine how far below this surface the ocean might be, with the hope being that if the ice crust is not too thick, then maybe one day we will have a probe land on the surface, drill through the ice, and go swimming in this very alien ocean, and hopefully be eaten by something with teeth, thus discovering life. Even Pluto, on the edge of the outer solar system, may have a liquid ocean inside. The universe, physics, likes building these things, and it may be the most common places where life exists in the universe are these sort of icy worlds. I really like the idea that somewhere in such an icy world there's a, I don't know, dolphin astronomer explaining to colleagues that it would be impossible to have life on the surface of a rocky body like the Earth. We're exposed to the sun, we have cosmic ray particles, the weather must be appalling. Well, you know, 1 out of 3. And you know, so there's a shift in perspective that came about from a simple discovery. And that's the excitement for me of this sort of discovery-driven research. You can find something unexpected and end up having to rewrite large chunks of textbooks. The other thing that I think is interesting about this is that it was a relatively, although the means of getting it were deeply technical, and the physics involved in designing the experiment and collecting the data and doing the data reduction and analysing it are complicated, at its heart the measurement is really simple. All they did was look for a change in the magnetic field, and astronomy is full of places where we can make simple measurements that have profound effects. So it's not that the things we're trying to do are complicated, we just have to do them really well. And this is a fun example. This is, you know, this thing about making simple observations goes back to the roots of astronomy as what hopefully lots of you did when you were walking in during the brief clear period, where you look up and notice something in the night sky. There's a beautiful crescent moon hanging above this building as we came in, and that's how I started astronomy. So I was looking at the sky. So this is a terrible picture of the twilight sky. So this is just after sunset, looking west, I believe. And it's a mostly blank sky with a landscape, but hopefully you can see just here, there are a couple of dots on the projector, ignore those. But here, that 3rd dot, just above my finger, that's real. It's an evening star in the sky. And if we zoom in on that in this particular picture, we discover that it's unusual, in that it's a double star. There are 2 bodies hanging there. That's because this image was taken on the surface of Mars by one of the rovers. And the evening star in the sky is the Earth with the moon hanging next to it. And so it's a simple observation, but it has profound consequences. And there's a whole lecture one could give at this point. If I felt like being Carl Sagan, you could do the whole, you know, everyone who's ever lived in humanity grew up and spent their lives on this one pale blue dot thing. But that's not what I want to talk about tonight. My own journey with astronomy came from simple observation like this. And in particular, when I was a kid, I had a small telescope that I'd purchased with money I raised selling ice creams on Torquay seafront in South Devon, a job I was terrible at. It's a whole other story. It's only a small telescope, I still have it, and it can't take pictures, but it can produce some nice views of the moon and the planets, and in particular of this, which is my favourite object. This is the Orion Nebula. It's our nearest stellar nursery, a place where gas and dust is being transformed into stars of solar systems. The great William Herschel, the discoverer of Uranus, the English observer, described this object as an unformed fiery mist containing the chaotic material of future suns. I wish we still wrote scientific papers like that. Nonetheless, it's an amazing object, and I like it particularly because even in a small telescope, even in the thing I could afford on my pocket money and Saturday job wages, it looks a bit like this picture. You can see this 3-dimensional structure. You can see the way the gas wraps round the new stars at its core. And the longer you look, the more you see. And so I've spent many, many hours staring through this telescope eyepiece, looking at the Orion Nebula. But there's one evening when I was about 15, when I nudged the telescope, and this cluster of stars just to the north of the nebula swam into view. It was striking, filled the eyepiece like this, and I'd never heard of a cluster of stars next to the nebula. This next bit's going to be difficult for younger members of the audience. I didn't have the internet at home at that point, but we did have books, which are like the internet but printed out. So I went and got my atlas of the sky, and I looked at it, and this cluster wasn't on the atlas. And I remember really clearly getting a pencil out and putting a cross and writing Lintott 1, because I thought I'd made a discovery. When I got to school the next day, got online, discovered this is actually NGC 1981. It's a cluster that was discovered in the 18th century. It's extremely well known, and still Lintott 1 to me. And the reason I'm telling you this is because I think for years I thought that was the point where I grew up as an astronomer. Because I think I realised then that I wasn't going to make a discovery with my back garden telescope from my back garden. And as I grew in the subject, got my degree, did my PhD, I sort of learnt that modern astronomy is done on a grand scale. I used during my PhD and when I first arrived in Oxford data from this telescope. This is the Sloan Digital Sky Survey. It's got a 2.5 metre mirror. It's in a site in New Mexico that is rather better than a back garden in Torbay. For starters, it gets 320 clear nights a year. And Sloan collected data literally on an industrial scale. It did an amazing thing. For 8 years, this telescope basically just let the sky turn above it and allowed objects, billions of them, to drift across its canvas. It took pictures of them as they did. And so it created a map of the sky. And then on the clearest nights, there were about 1 million of these objects that were galaxies, systems like our own Milky Way. And on the clearest nights, it went back and it measured the distance to those galaxies. So we had not just a 2-dimensional map of the sky, but a 3-dimensional map of the local universe. And I can show you that. We're going to start on the Milky Way, and we will travel outwards through this survey. It was our first really large-scale look at our local universe. This is about half the data, so it's about 500,000 galaxies in this simulation, or in this visualization. And so I want to say this isn't just sci-fi. These are the real galaxies in the right place. So this is data. And you can see it's a remarkably rich data set. Each of these galaxies, as they fly past, has had a complicated 13 billion years of merging and interacting with their surroundings. You can see, as we get further out, that the great truth that we got from the Sloan Digital Sky Survey was that the universe is lumpy, that there are places on large scales where there are lots of galaxies and places where there are very few. There's a C-shaped structure on the left here, which is the Sloan Great Wall, which is the largest thing that we know of. There are areas with very few galaxies, which are called cosmic voids. And this is an incredibly rich data set. There's a shared resource for all astronomers, and indeed anyone who's interested. You can go online, you can get the data from Sloan, and analyse it to answer your own research questions. But mostly, why this data was taken was to write papers like this one. This is the completed SDSS-4 extended baryon oscillation spectroscopic survey, measurement of the area, growth rate of structure of the emission line galaxy sample from the anisotropic power spectrum between redshifts 0.6 and 1.1. Now, I know many of you will be familiar with this. The point is, what people mostly did with that data was to take all those images of galaxies and all those measurements of distance and put them in a bucket and do complicated statistical things to them in order to make this graph. And this graph is, the wiggles in this graph are a way of measuring the expansion rate of the universe. So how fast is the universe expanding? And this is fine. I'm happy that they did this. And indeed, the survey got published, got paid for, because people wanted to do this one measurement. But I just think it's also a scientific process to notice that one of the galaxies looks like a penguin. Because that's just as important as well, right? Because you've got immediate questions like, why does it look like a penguin? Is the egg anything to do with it, or is that a coincidence? What are these dust lanes? Why is it blue around the edges? Well, that's a place where stars are forming, but why are stars forming only on the edges of this galaxy? You could do a whole PhD on this one penguin galaxy. In fact, I know somebody is, because just the other day we got a James Webb Space Telescope image of the penguin. This is now in the infrared, and some mysteries have been cleared up. You can see the egg is connected by a bridge, so those are interacting galaxies, and you can see the red areas here, which are star-forming regions. There's a lovely feathered effect, I've got to admit, but you can see there's this cluster here, and I think what's happened is that this other galaxy has ploughed through and created a disturbance which led to this shape. Both kinds of science are important, the planned, the systematic, the route to measurement, but also we get discovery, and we get new questions from noticing, from making simple observations. And I think when you look at the history of astronomy, that sort of making observations and being surprised by the universe has echoed throughout the history of the subject. One really good example goes back to the early years of the 20th century and the discovery of the science of radio astronomy. Radio astronomy wasn't started, the idea that you could pick up radio waves from objects out there in the cosmos wasn't started by astronomers. The first radio astronomer, pictured here, was a man called Carl Jansky, who was an engineer employed by Bell Labs, who had just launched in 1927 the first transatlantic telephone service at what was then $75 a minute, which must be, what, tens of thousands now? But it involved a radio link, and the quality was terrible because of interference from all sorts of background sources, the crackle and hiss that you get from a detuned radio. Jansky's job was to determine what sources of interference there were. He built this marvellous instrument. So this was known as his merry-go-round. It's a bunch of radio antennae that he could rotate using the wheels stolen from a Model T Ford. But the rotation is important because if you can rotate your antennae, then you can work out what direction something is coming from. And so the idea was to look for individual sources of noise and then rotate and work out where they are. And he found pretty quickly that most of the noise that was interfering was coming from distant thunderstorms, often hundreds or even thousands of miles away. So you could correlate the electrical activity of our atmosphere with his observations. But once he'd accounted for them, he found there was another source of noise. And originally, he thought it was matched the location of the sun in the sky. So he thought he'd discovered that the sun emitted radio waves. But over the course of many months, this extra radiation detached itself from the sun in the sky. By talking to a friend who was an astronomer, he realized that what he was seeing was radiation from our Milky Way, from the disk of our galaxy, as it seems on the sky. And it was brightest at the center of the Milky Way. And so he realized that he picked up cosmic radio waves for the first time. He called what he was hearing star noise, which is a bit of branding we should bring back. I think that's lovely. He got a master's thesis for writing this work up. He knew that he knew he'd stumbled on a new kind of physics. He knew, for example, that whatever this star noise was, it couldn't be coming from normal stars, because he knew that normal stars are objects rather like our sun. And if all stars emitted radio waves, then surely you'd see a stronger signal from the sun than from the Milky Way. And so he knew that there were other sources of radiation out there in the cosmos. We now know that some of what he was seeing came from exotic high-energy objects. Some of it came from the black hole at the center of the galaxy. And so he was right about this. But Jansky, having published this work in 1933, was moved on by Bell Labs. There's some dispute in the record as to whether he chose to move on or whether his bosses decided that he should do something more commercially useful. And he worked for the rest of his life on military projects and more commercial applications. He did, however, inspire one important person. The star noise was played on the radio in the US. I have a long-term project. I'm assuming it was also played. It was news here, it was in the papers in the UK, and I'm assuming that the nascent BBC also broadcast star noise, but I can find no record of it working on that. Anyway, it was played on the radio in the US, and it was heard by another engineer, a guy called Vera Rubin, who decided that he wanted to work on this. He wrote to Jansky and asked work with him, and Jansky said, well, I'm not, Bell Labs are doing nothing more with this. And so Jansky decided to go it alone, and he built the world's first radio telescope. This is the world's first radio telescope. It's a dish that's nearly 10 meters across. Reba lived in suburban Illinois. He used to commute to work in Chicago and then come home and do his astronomy in the evenings. This is his mother's garden. He obtained permission to build the radio telescope in her garden if during the day she could hang her washing on it. It's lovely. And a fine example of collaboration between scientists and non-scientists. Reba's an astonishing person who deserves a whole lecture. With this telescope, he managed to map for the first time the Milky Way. So because it has a dish, it has better resolution. He was able to discover, for example, that our galaxy was a spiral galaxy, just like those that had been seen in the sky. The astronomers didn't care. He sent a paper to the Astrophysical Journal, then as now one of the leading journals, and instead of accepting it, recognizing it as a major piece of work, they sent a delegation of people to find out who he was and whether he was serious. A bunch of optical astronomers, people from observatories and universities turned up here. The only record we've got of the visit is that they said it all looks very modern. And I'm not sure that was meant as a compliment. They sat on his paper until Reba eventually complained that they'd let it moulder. And it was eventually published. Here are his maps of the galaxy. But he was basically ignored by the astronomical establishment for much of his life. He was independently wealthy enough and frugal enough that he could fund his own research. And he went on to do all sorts of amazing things, including publishing a seminal paper that shows that parrots in Hawaii are left-clawed rather than right-clawed. That's a whole other story. He ends up in Australia, in Tasmania, where he builds an electric car in the early 70s. It covers his house in aluminium foil to save energy. He's built his own radio telescope by this point, and he has his own cosmology, his own theory of how the universe began. And yet he can't quite prove that he's right and everyone else is wrong. And he decides, this is an extract from another lecture that's appeared, but it's such a good story, I'm going to tell you anyway. He decides that the thing that's interfering with his measurement, the only thing that's stopping him being proved right, is the Earth's upper atmosphere is in the way. It's interfering with the long-wave radio measurements he wants to make. And so he comes up with an ingenious solution, which is that he writes to the Australian government and he asks, in his words, to borrow an intercontinental ballistic missile. Because he thinks if one of these is flown above his house through the upper atmosphere, it will clear away the interfering layer, he'd be able to see the distant universe, and this would prove him right. They don't lend him an ICBM, but he has enough sway, and his contributions to radio astronomy were recognised, that in 1985, when the Space Shuttle Challenger flew over his house, it deliberately fired its engines to see if it could affect the upper atmosphere. His results still didn't confirm his theory, and he blamed NASA for firing the engines wrong. He's an amazing person. But between Jansky and his star noise, Reba, an amateur from outside the field who knew enough about the technology and educated himself, a whole new way of doing science was formed. And I don't really have time to talk much about modern-day radio astronomy, but there is one great example of serendipitous discovery from the last few decades. This is the Parkes Radio Telescope. This is Australia's Jodrell Bank, although they hate it when I describe them as that. This is the dish. If you've seen the film, this is a radio astronomy telescope that was involved in bringing back the pictures from Neil Armstrong's first small step onto the lunar surface. There was an astronomer called Duncan Lorimer who in 2007, working with a student, was going back through archived observations taken 6 years earlier from this. And they found in those observations evidence of a burst of radio waves that had appeared and then disappeared very quickly in a random part of the sky. Astronomers are bad at naming things, so this burst of radio waves that appeared and then quickly disappeared was called a fast radio burst, which at least does what it says on the tin. Once you find an unusual object, of course the next question is, does this happen often? And so now they knew that this was possible, a team at Parkes went back through the data and found many other examples, about 30 examples of similar bursts of radio waves coming from all over the sky. the sky is really interesting, because if these were local phenomena, they belong, for example, to the solar system, then they should follow the zodiac, the ecliptic in the sky. If they came from our galaxy, they should follow the Milky Way. But they come from all over the sky, which means they're either very close, or they come from the distant universe. And if they come from the distant universe, then these are very powerful events indeed for them to be detected. This larger collection were a complete mystery. People suggested everything from alien spacecraft in distant universes to the strange effect of lightning in the upper atmosphere of the Earth. About 30 papers were published on this sample. And eventually, the astronomers at Parkes, about 2015, received an email from a retired engineer who said, I know what these are. What time of day do they happen? And this is a really bizarre question to ask. If these are explosions in the distant universe, it should not care what time it is in Eastern Australia. Right? If I believe one thing as an astronomer, I think I believe that. And yet when you make the plot, which no one had thought to do, this is when they happen. They happen roughly between about 11 o'clock in the morning and about 3 o'clock in the afternoon. And so they emailed back, and the retired engineer said, yes, I used to work on microwave ovens. And this is a malfunctioning microwave, and it was in the visitors centre. You know, if you get impatient and you open the door before it goes ping, your microwave has a safety setting that cuts off. This one was malfunctioning. So whenever anyone was impatient at lunch, they would produce a celestial phenomenon that was recorded. And I know one person who spent a very happy summer at Jodrell Bank destroying microwaves to see if they could reproduce the effect. And it became clear that what the astronomers would be doing was detecting lunch, except that first burst that Lorimer found was real. And observatories around the world have now looked for and found fast radio bursts. This is the Chime telescope in Canada that was built for a completely different purpose that has now found about 5,000 of these things. But these fast radio bursts in the distant universe are real. We don't know what causes them. There are currently, well, as of 6 months ago when we published the 52nd possible explanation, there were 52 explanations in the literature of what they might be. It's probably something exotic involving magnetic fields, but who knows. These things are strange. They come from distant galaxies, but we have seen one in the Milky Way. They seem to be one-offs, except some of them repeat. They occur at all frequencies and at different timescales. And they're a proper astronomical mystery. And microwaves aside, they were found by an undergrad project to just look and see if there was anything interesting in the archives. It's another example of serendipitous astronomy. Of course, if I'm talking about discoveries in radio astronomy, I think where people expect me to go is to talk about SETI, to talk about the search for extraterrestrial intelligence out there, because we've long expected, see Jodie Foster in Contact from 1997. Radio astronomers don't really listen to data like this, but never mind. People expect me to be talking about life, because we've long expected there to be the discovery of intelligence in the universe to come via an unexpected source of radio waves. And that's true, and that's a valuable effort that we're working on in Oxford. But actually, one of the things that shifted is I think we're now thinking more broadly about how to be conscious that there might be other signs of life out there, and how we might use this search for unusual things to tell us about life in the universe. I had an adventure in this about 10 years ago. So one of the fundamental things that we've learned about the universe in the last probably decade or so, maybe a little more than that, is that when you look at a starry sky like this, when you walk out into the undoubtedly beautifully clear night that awaits us out there, and you look up at the night sky, you should know that most of the stars that you're looking at probably have planets going around them. We've learned that planets are common in the universe, something we didn't know until recently. I can even show you some of them. This is a video from the Very Large Telescope in Chile. I told you astronomers were bad at naming things. We're building the Extremely Large Telescope to replace it. And this is a nearby star called HR 8799, but it's it's via an instrument called a coronagraph, where we remove most of the light from the sun. The yellow thing has been added back in as a placeholder. That's not what stars look like. But the 4 dots around it are real, and those are planets in orbit around the star. And I love this image because you've seen an animated version of this many times. Every TV show you've seen about astronomy, any lecture you've seen about astronomy has the animated solar system. But this is the real thing. We're watching planets around an alien star. And while we can only see these planets because the star is nearby, because it's faint enough that we can do this trick of getting rid of its light, and because the planets are young, so they shine brightly, we know the planets are common because we found simple observations that allow us to detect them indirectly. So this is the sun, which many of you may remember. And this is a video from a particular day in 2012, taken from a beach in Queensland by Jamie Gilbert, who was a PhD student here once upon a time. And on this particular day, Venus passed in front of the sun in what's called a transit of Venus. These events are rare. The next one will happen in the 22nd century. And it's rather nice to see the video of Venus shooting across the sun. On the right is sort of the physicist's version. This is just the output from a light meter we stole from a lab that just measures the brightness of the sun. And so when I talk about simple observations, the physics here is simple. When Venus is in front of the sun is a bit fainter. Yeah? Of course, you have to play this game and you have to make that measurement precisely. But if you watch enough stars carefully enough, then you'll find that some of them blink. And they blink when a planet gets in front of the star. And if you wait, the planet will go around complete an orbit, and then you get another blink, and then you get another blink. This repeating pattern allows us to work out that there's a planet there. And also, you can see we can guess at the size of the planet, because we know how much of the star's light is blocked, and we know how long its year is. So we get the sense of what this planetary system is. Mainly this has been done with space telescopes, with a mission called Kepler. Now there's one called TESS. And the data is noisy enough, and the task of spotting those dips complicated enough, that my team here have put all the data online on a website called Planet Hunters, and we've invited anyone to come and help us sort through the data and find a planet. But the nice thing about having people look at your data is that you can be surprised. And the most surprising thing that was found was a star called KIC 8462852. You can tell this is an exciting graph because I'm going to reveal it in stages. And so this is the brightness of that star over about the 3 years that the Kepler Space Telescope studied it. So you can see just after it started observing the star, there was a dip in brightness. That could be a planet. It could be a large one, given the size of the dip, but it could be a planet. And in fact, there is a second dip, but no third one. And so it's not clear what this is, but it's not a planet. Planets don't go around once, twice, and then choose a different orbit, or go on holiday, or turn up late, or anything. That's not what they do. So maybe this is something to do with the star. Maybe it has a star spot for a bit, just as the sun has sunspots. No one paid any attention until about a year later, when our volunteers on Planet Hunters noticed that the star had dipped dramatically. Just for a day or two, it lost about 20% of its brightness. And then it came back to full brightness and carried on as if nothing had happened. And stars don't do this. No other star in the 200,000 or so that Kepler was looking at ever did this during the 3 years of the mission. And so the volunteers started paying attention, and they were really paying attention a year and a half later when the star did this. It was like somebody got hold of a dimmer switch and was flicking with it. It faded, it brightened, it faded, it brightened. It had these long dips down to about 2/3 of its previous brightness, then it came back up, and it was still misbehaving at the end of the mission. The volunteers called this the WTF star. They asked us what we thought about it. We didn't know. And in work led by my colleague Tabby Boergen, who's now at Louisiana State, Tabby and her team spent about 6 months trying to work out what this might be. We thought about whether the star was unusual. We went and observed it. The star seemed to be a perfectly normal middle-aged star. We thought maybe it was a technical problem. There was an awful week where we spent a week trying to work out which pixel of the camera had taken every single one of these data points, in case there was a weird pixel. We thought it might be something local in the solar system, maybe a dust cloud or something, so we looked at neighbouring stars. And we couldn't come up with anything, so we wrote a paper and and sent it to the journal to just say, look, we found a weird star. And the journal editor wrote back almost immediately and said there are two problems with your paper. Problem one is that you've called it the WTF star. And all acronyms need to be spelled out in the journal. So WTF stands for Where's the Flux? Very clear. And then the second thing, which I still disagree with, was, and by the way, lots of these people are volunteers who had led the early, including Darrell LaCourse, who's the second author, who led a lot of the work. So the other problem is you haven't explained what this thing is. And we said, well, we don't know. He said, well, to be a scientific paper, you have to have a hypothesis. You can't just say you found a weird thing. And so we sort of scratched our heads, and we came up with the idea that maybe this was a comet. And comets have many advantages. One is that they don't, for example, give off infrared light. You can hide quite a big comet around the system and not have it otherwise detected. The other is that comets are known to break up. They go on long elliptical orbits around their star, in the solar system, for example. And they're made of ice. And so as they swing past the star, or in our solar system, the sun, they heat up and sometimes break up. This is a 19th century woodcut of Comet Biela, which was a famous comet that came around every 8 years. Then one time came around and there were two of them, and then it didn't come round the next time. And then the time after that we had a beautiful meteor shower. So this is a comet that had been broken up. So we said, okay, so what's going on around this star is, here's an unconvincing artist's impression of this. But we said, okay, there's a comet around the star and it's broken up into pieces. So there was a bit, and then another bit, and then a big bit, and then a whole swarm of what I'm delighted to tell you are called cometlots, small bits of comet. And this is a good enough idea. It has the disadvantage that you can explain any pattern just by moving bits of comet around. So, is that a scientific explanation? Not sure. We also immediately, when we published the paper, we immediately heard from everyone in the world who studies comets, who told us how big this comet would have to be. It's 10,000 times larger than the largest comet ever detected. And it would have had to have broken up just 2 years before we happened to look at it, and et cetera, et cetera. It was considered implausible. We got our paper out, and what started to happen was that astronomers like a mystery, as you may be gathering, and other astronomers started to publish ideas as to what this might be. The one that caught attention was this paper. This is the Jihad Search for Extraterrestrial Civilizations with Large Energy Supplies, paper 4. I'm going to assume you've read 1 to 3. The signatures and information content of transiting megastructures. And the idea here is that this star is surrounded by solar panels. That the aliens who live in the star system have decided to get their energy from the star. They've launched fleets of solar panels, and those solar panels are blocking out, so stellar panels would be better, are blocking out the light from the star. And so every time we see a dip, it's because a part of their alien solar panels has gone away. It's an old idea. It goes back to the Oxford science fiction writer and philosopher Olaf Stapledon. It's more commonly known as a Dyson sphere or a Dyson swarm. And Jason Wright, a friend, said, this is what you might have found. And I found out about this paper when I picked up my phone at 9 o'clock in the morning in the office, and a voice at the other end of the phone said, hello, this is the Daily Mail, we think you found aliens. And I'm not great at 9 o'clock in the morning. And so I just told them to go away. I said I'd call them back, and then I started trying to work out what was going on. But here's the question, have we found aliens? It's got the same problem as the comet hypothesis, in that I can explain any pattern just by moving my alien solar panels. But we did feel a need to test this idea, so we kept an eye on the star via robotic telescopes like this one in Hawaii, and eventually, 2017, the star dipped again. And this time, we were ready. About 100 telescopes, amateur and professional around the world, pointed immediately at the star. And we discovered something we didn't know, which is that if you had a camera that was sensitive to red light, you saw a dip. If you had a camera that was sensitive to blue light, you saw a dip. But it dipped more in red light than in blue light. And so what that means is it's not a solid object. Whatever's blocking out the light from this star is probably something more like a cloud of dust, rather than an alien solar panel. So we're sure it's not aliens. But we still don't know what it is. And actually we found many more stars that misbehave in this way, because once we found one, we knew to look for them. I should wrap up. I've told you a few stories about scientific discovery and how it actually happens. And the thing that common about them is that great science gets done from stumbling over something. An alien ocean, a misbehaving star, the science of radio astronomy. But I don't want you to think that the stumbling is easy. You have to have collected the data in the first place. And then the crucial thing is that you have to be so well versed in your science to have an instinctive knowledge of what's unusual and worth paying attention to. The person, of course, who did this best is Jocelyn, because this is exactly what happens with the pulsar discovery, where what many people would have passed off as noise in a signal to Jocelyn looked unusual. And she was somebody who knew the experiment intimately, knew the data intimately, and thus knew that this was something worth following up. And we got the great science of pulsars and what came from that because of that work, even though the moment of discovery was an accident. And the reason I wrote the book that talks about this stuff, and the reason I talk about this stuff with my colleagues, and the reason I'm working on finding unusual things is that I think we're going to need to do this really well in the near future. There is a telescope in Chile that's just about to go into operation. This is it. This is the Vera Rubin Observatory, named after a great pioneer of studying the structure of galaxies and the universe. And Rubin is an astonishing instrument. We've been involved in this project in Oxford for about 20 years, designing the camera to planning the science and so on. It's a special thing. It's as big as the biggest telescopes in the world today, with an 8 and a bit meter mirror. It's got the world's largest astronomical camera. Here it is being hoisted into position. This is a 4,200 megapixel camera. But what's special about Rubin is that it's going to scan the whole sky every 3 nights. And so by adding up that repeated observations, we will get deep images. So here, for example, is a part of the sky from Sloan, from that survey that we flew through. I'm going to show you a test image from a month's worth of Rubin data. And this is going to be a 10-year project. So this is what we had before. This is what we're going to get from Rubin. It's a completely different universe, and this isn't the exciting bit. Because the exciting bit is that as we scan the sky every 3 nights, Rubin will send out an alert every time anything moves or changes in the sky. And they'll be public. Anyone can subscribe to these alerts, but if you do, when you wake up, your phone's going to have about 10 million alerts a night on it. And this stream of data, I don't think I'm allowed to tell you this, but that stream of data we think will start on Monday. And in there will be the flickering of stars because planets getting in the way, all the sorts of variability that stars have. We'll see nearby galaxies flicker because material's falling onto their black holes. We'll see more supernovae, more stellar explosions in the next month than we've had in the rest of human history. We'll have exotic objects as material falls onto black holes, and black holes collide, neutron stars merge. But in that stream of 10 million alerts, I will bet you almost anything that there are types of object that we've never even dreamed of. And our task is to be alert enough, to know the data well enough, that when we stumble across them in the next few weeks and months, we'll recognize that they're interesting. And I hope I get to come back and tell you about some of the stuff we've discovered in a few years' time. Thank you very much.
Thank you, Chris, for a really awe-inspiring talk. There are so many people here and so little time that I'm not going to ask any initial questions because I think that wouldn't be fair. I'll ask you what I thought from other people's questions later.
Okay.
But I'm just going to open it up and say, Chris has got some time to take some questions. Who's going to start? Put your hand up and please wait for a microphone. Okay, I've got Steve down here.
It's always best after we have a question at the front, if somebody in the back can ask the next one, just so people get exercise, that would be great.
Thanks, Chris, for a marvellous talk. Can I ask you about something you said right at the beginning?
Sure.
Which was about the rings of Saturn and their age, because I understand this has been quite controversial, whether they go back all the way to the origin of Saturn 4 billion years ago, or whether they're much more recent, as you say, a few hundred million years ago. This has been quite controversial.
Yes, yes.
So what's changed?
Yes, and it's important. So whether the rings of Saturn are common or not, or whether they're recent or not, may seem a bit obscure as a thing to talk about. But it's important because it tells us whether they're unusual or not. Because if they're recent, they could be a sort of one-off event, and maybe they're our solar system's greatest tourist attraction. So there was a brilliant paper out 2 weeks ago which looked at Titan, that moon with the atmosphere and so on. And it turns out, it's a synthesis of things, but Titan's atmosphere looks like it's young. So it's only a few 100 million years old. You could tell that from the chemistry of the atmosphere. And then Titan's surface doesn't have almost no craters on it. And so that means it's fresh. And so if you tie these two things together, this was a theoretical paper that suggested what had happened was there'd been a collision. So Titan had collided with another moon. That explains what's happened to Titan, but the leftovers form the rings. And I think it's really convincing, and I thought it was astonishing to learn something new. We need to get back to the Saturn system to test this. There's a mission called Dragonfly that's going to go and fly around. It's a little helicopter that will fly around in this orange atmosphere of Titan. And I think we'll know more then. But yeah, that's the idea.
Can I ask you a question about, because I love Saturn.
Yes.
I liked it. But we had a graduate physics student talking here last night, and there were sort of unexplained phenomena with sort of jets shooting out of them. Why does the ring go around that? Why if a moon exploded, why isn't it a layer right round Saturn? Why is it in a sort of disk?
So the universe likes making spheres and disks. And if you've got a sphere, it's because gravity is important. So if you have lots of stuff, then gravity will pull whatever system we're talking about into a sphere. So that's why, for example, it's used as a test of what makes a major planet. You have to be spherical because it's a way of measuring mass. If you're spinning, then you end up in a disk. And so really, from a physicist's point of view, the fact that the rings are a disk tell you that rotation was more important than gravity. Because even though there are billions of icy particles, there's not much mass there. It's probably much less. It is much less than our moon. And so that's why. But yeah, you could think of the universe as just an assemblage of spheres and disks, basically, controlled by this physics. Microphone coming across the thing.
Yes. And can you hold the microphone quite close to your mouth so people can hear? They're not. Thank you.
Thank you. If you could pick one astronomical satellite to go up in the next 10 years, which one would that be?
Oh, this is going to make me enemies amongst most of my friends. I'll give you a slightly mad one that I don't think anyone's agreed to fund yet, but I think is a lovely idea, which is that though we talk about these planets around other stars, we can't see most of them. The ones I showed are an exception. And if we find an Earth-sized planet that's sort of in an Earth-like orbit around a nearby star, it's heartbreaking not to be able to see it, even if it's just as a dot in the sky, like that image from Mars. So the game is, what you do is you launch a modest space telescope, something maybe the size of Hubble. But instead of keeping it around the Earth, you send it to the edge of the solar system, maybe an orbit that's rather similar to Pluto's. And then you look in the direction of the sun and use the sun's gravity as a natural telescope to magnify what's happening behind. And if you do that, you should be able to get an image of an Earth-like planet around an Earth-like star. And so you have to do this mission and you get one image. But even knowing the color of that planet, for example, would allow you to distinguish between a Mars-like world or an Earth-like one. And I think that would spur an enormous amount of art and science just from that one image. So it's probably $1 billion mission, or these days €1 billion mission, as we're more likely to fund it than the Americans. But I think that would be worth it. So yeah, we'll go for that, please. We know how to do it. That's the crucial thing. We've just got to afford it.
Thank you. Well, last week I saw this really interesting article and I thought it was incredibly topical for this talk. It was about, it was again about kind of the accidental discoveries and things. And I think they were trying to look for signs of life towards the center of our galaxy, and instead they stumbled upon pulsars that were spinning at incredible speeds, and they want to try and use this to study general relativity and all of those effects. And I guess my question is quite an open one about, you were talking a lot about looking for other types of astronomical things, and then people thinking, oh, could that be a sign of life? And I guess this is sort of the reverse of that, looking for signs of life and then discovering other things and discovering lots of new physics. So what were your thoughts about like that collaboration between all the different worlds of physics?
I think it's really exciting, and it's something I've sort of stumbled into because I was trying to find planets, and then we ended up thinking about whether this could be aliens. And we now have, actually in the department, we have a group called Breakthrough Listen who think about ways to look like. But one of the great things that have happened is that technology has meant that you don't have to choose. So we now have instruments that can sit on the back of radio telescopes and just listen along wherever that telescope's pointing, whatever work it's doing for its core astronomical purpose. We can be looking, for example, for regular signals that might betray intelligence or something like that. So in the past, the problem has been getting access to radio telescopes to do the more speculative stuff. But because computers have got better, we can now do both at once. And I think that's a really good example of how you could sort of play this game. The Sloan survey that I showed, they wanted to make their graph and measure the expansion of the universe, which is great, but they took pictures of their galaxies, so we get to do our penguin science as well. And if they hadn't taken pictures, then we wouldn't be able to do that. So I think there are lots of ways to tweak what we're doing so as to increase the possibility of serendipity. And one important one is actually just to make the data open, to let anyone who wants to play with it, use it for whatever purpose, rather than keeping it to ourselves for our particular purpose. That's really important. Thanks for the question.
I didn't ask you about the machine learning bit of your expertise. I mean, if we look at how machine learning has enabled us to, unpack how proteins work in a way that would have taken months and years for each one, just, okay, we know how to do this now, we can just do it systematically. Is this going to happen with astrophysics, or is the data too strange, we don't know what we're looking for enough to do that?
Well, machine learning is definitely useful. I think we have different requirements from a lot of the use cases. For example, we care about the 1 in a million object, whereas if your Google AI gets 1 in a million wrong, then maybe they don't care. I think one of the most interesting things in my work in machine learning is that we find that saying, if you've got, I don't know, a million images of galaxies, saying which are the most unusual is a thing that machine learning can do really easily. It turns out to be very tractable as a problem. But saying which of the unusual galaxies is interesting is disastrous. That's a human thing. And so that's the collaboration for the Rubin data. That's what we're trying to build. If we can filter that 10 million objects to say the 100th most unusual, then that's tractable for one of us to look at. Whereas if we have to look through 100,000, we're toast. So that's the way we're looking at it. It's sort of that insight comes from humanity, but the bulk filtering of the boring stuff is the machine's perspective.
We've got time for one more, if anyone has a burning question. Yes, just here.
Thank you for the talk. I'm did a science undergrad and I'm no longer involved in the field at all. And you really brought back a sense of that joyful, almost childlike curiosity that I think got me involved in science at an undergrad level in the first place. And I guess just a personal question on, you described that kind of that feeling of awe when you discovered Lintott 1. I just wondered what other moments like that have stood out across your years in the field.
I had one recently, actually. They don't come very often.
Lintott 2.
Yeah, we're still working on the nomenclature. But one of the things I've got involved in, because I think it's fun, really, is studying interstellar objects, so comets from beyond our solar system, of which we think in the galaxy there are a billion, and of which before last summer we had seen 2, which is bad even for us. But we found the third one last summer, an object called 3I Atlas. And because of the work that we've been doing, I had a poor PhD student, Matthew Hopkins, who literally handed in his thesis on the properties of interstellar objects the night before the third one was found, which is, as I said to him, the only thing worse than that is handing it in the night after. So anyway. So he literally sent me an email saying, I'm going on holiday for 3 weeks. I said, great idea. And then I called him at 6 o'clock the next morning and said, no, you're not. Like, we've got it. And it was sci-fi science. We were on immediately deploying telescopes and talking to our colleagues and so on. But there was a point, because of the work that Matthew had done, we were able to calculate the age of this thing. And he came into my office and he said, oh yeah, it's between 9 and 12 billion years old. And I said, all right, fine, wrote that down and went back to the work I was doing. And then 3 hours later, I stopped dead. And my brain just went, that's older than the solar system. And so we realized this thing that we could see in the sky is older than our solar system. It's the oldest thing we've ever seen close up. And I went out that night and I drove to a friend's house who has a powerful enough telescope that I could see it. It was just a dot, but I could see the oldest thing we'd ever seen. And it wasn't the moment when he told me the number, it was the moment my brain processed it. That was cool.
Does it make you feel insignificant?
Yeah, but that's useful. You know, it is a way of, there's a sort of, I think people sometimes have the impression that I have some deep understanding of what it means to live in a universe with hundreds of billions of galaxies, each containing hundreds of billions of stars. But I'm as boggled by that as anyone else. We've just got used to saying billion. But I think there's, you know, out under a night sky, think about all the planets. I think my email inbox shrinks and the problems and the worries go away. And I actually think that's quite useful. So yeah, insignificant, but in a reassuring way.
Well, thank you for showing us some things that are really significant in a reassuring way at the end of the week. Thank you for reminding us of what's joyful and exciting about learning, and also reminding us that human beings are the people who decide what's interesting. And if there's one thing we're trying to do with these talks, it's saying, here's lots of things, which ones do you find interesting? I'm afraid next week we were going to have Lord Hermer, who's the Attorney General, talking about advocating for the rule of law, but he's too busy doing it. He's promised to come back, so if you signed up for that one, we will let you know when he comes back, which will be next academic year, I think, or later this academic year. But on the 6th of March, continuing our celebration of women in traditionally male-dominated careers, we have a relatively young Mansfield alum, Sarah Jahan Khan. It's International Women's Day talk. And she's going to be showing us a film she made called Wood, Spice and Dough about women in Hunza in Pakistan who are working in traditionally male-dominated careers there as chefs and carpenters. It's a brilliant film, so do come along to that if you would like to. But in the meantime, thank you all very much for showing up on a night that may not be that clear when you go out and try to look up in an awestruck way. But anyway, there's too much light pollution in Oxford to do that anyway, so you'll just have to go and look online. But thank you all for coming, and thank you, Jocelyn, for letting us name a talk for you, and Chris for giving us such a fantastic Jocelyn Bell Burnell Lecture. Thank you.
Thank you.